Hi, Stu Schwartz, MasterMathMentor.com. This is video BC Non-Essential 5a. The topic is Simpsons Rule, and it covers the BC manuals, pages 152 through 154. In using Riemann sums to approximate areas under a function f of x, we are creating rectangles. A rectangle draws a horizontal line at various locations on the function. Horizontal lines are 0-degree functions. So a right or left Riemann sum, as shown in the figure we're using a right, draws 0-degree functions at various locations on f of x. So for every rectangle that we draw, there is an error associated with the rectangle. And unless we have many rectangles, the summation of the errors will be large, and the area approximation will not be good. When we use trapezoids to approximate the area under a function f of x, we draw lines that are usually not horizontal. Lines are first-degree functions. So a trapezoidal rule, as shown in the figure, draws first-degree functions between points on f of x. Again, for every trapezoid that we draw, there is an error associated with that trapezoid, albeit much smaller than we have with 0-degree functions. Still, if we are integrating over large areas, these errors can add up, requiring more trapezoids, and thus more work. So, continuing the analogy, if we take this process one step further, we can approximate f using a series of second-degree functions. These would graph parabolas, and the curvature should ensure that the error will even be smaller, meaning that fewer parabolas would be needed. This process is called Simpsons Rule, named after the English mathematician Thomas Simpson, who lived in the mid-1700s. Suppose we have a continuous function passing through the points 1, 1, 2, 3, 3, 2, 4, 1, 5, 3, 6, 5, 7, 2, 8, 1, and 9, 7, as shown on the graph. In your manuals, very lately, draw 4 parabolas through the first 3 points, points 3 to 5, points 5 to 7, and then the last 3 points. We will now try and generate equations for these 4 parabolas, remembering that a parabola is in the form of y is equal to ax squared plus bx plus c. So we will work with our first 3 points, 1, 1, 2, 3, and 3, 2, and plug them into the equation y equals ax squared plus bx plus c. We end up with 1 equals a plus b plus c, 3 equals 4a plus 2b plus c, and 2 equals 9a plus 3b plus c. We can solve these simultaneous equations by algebraic methods, but it is far easier to use matrix theory. So we first put the coefficients of a, b, and c into a 3 by 3 matrix, which on the calculator we will call matrix A. So the first row has the coefficients 1, 1, 1, the second row 4, 2, 1, and the third row 9, 3, 1. We will next put our left side coefficients into a 3 by 1 matrix, which we will call on the calculator matrix B. So matrix B consists of the numbers 1, 3, 2. The magic formula to solve the simultaneous equations is A inverse B. So we will calculate A inverse B, on the calculator, and the resulting matrix gives the coefficients of the quadratic a, b, and c. We get negative 1.5 as a, 6.5 as b, and negative 4 as c. To show that we are correct, we will input the quadratic into the calculator with the conditions that x is greater than or equal to 1 and x is less than or equal to 3. So our equation is y1 equals negative 1.5 x squared plus 6.5 x minus 4 divided by the expression x greater than or equal to 1 and x less than or equal to 3. Assuming our points have been put into the calculator and we have indicated that we wish to graph them, we can use a zoom 9 to show the points, and we'll then get the resulting equation graphed between 1 and 3. And we can see visually that this is correct. So, for parabola 2, joining the points 3, 2, 4, 1, and 5, 3, our equations are 2 equals 9a plus 3b plus c, 1 equals 16a plus 4b plus c, and 3 is equal to 25a plus 5b plus c. Doing our matrix work, we get y is equal to 1.5 x squared minus 11.5 x plus 23. The third parabola joins the points 5, 3, 6, 5, and 7, 2. Our equations are 3 equals 25a plus 5b plus c, 5 equals 36a plus 6b plus c, and 2 is equal to 49a plus 7b plus c. And our resultant work with matrices gives the parabola equation y is equal to negative 2.5 x squared plus 29.5 x minus 82. Finally, the fourth parabola joins the points 7, 2, 8, 1, and 9, 7, giving the equations 2 equals 49a plus 7b plus c, 1 equals 64a plus 8b plus c, and 7 is equal to 81a plus 9b plus c, and our resulting parabola equation is y is equal to 3.5 x squared minus 53.5 x plus 205. We graph all four equations on our calculator just to be sure that our equations pass through the required points. Now that we have our four equations, we can use four integrals to find the area under the curve and sum them. So, the integral from 1 to 3 of negative 1.5 x squared plus 6x minus 4 dx is 5. The integral from 3 to 5 of 1.5 x squared minus 11.5 x plus 23 dx is 3. The integral from 5 to 7 of negative 2.5 x squared plus 29.5 x minus 82 dx is 8 1/3. And the integral from 7 to 9 of 3.5 x squared minus 53x plus 205 dx is 4 1/3. So therefore, the integral from 1 to 9 of f of x dx is approximately 5 plus 3 plus 8 1/3 plus 4 1/3, which is 62/3. Notice that this is still an approximation, as we don't know values of x between the given points. This is a great deal of work. Determining the equation for each of these parabolas takes time, and then we have to integrate them as well. Simpsons Rule really simplifies things. It states that if we have some f of x on the interval a to b that is divided into an even number n of subintervals of equal width dx, then we can express the integral from a to b of f of x dx as the approximation 1/3 times the quantity b minus a over n times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4 plus ... plus 2f of x sub n minus 2 plus 4f of x sub n minus 1 plus f of x sub n. This seems complicated, but it really isn't. Just as with our trapezoid rule, we had multipliers. 1, 2, 2, dot, 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 2, then back to 1. Simpsons rule also has multipliers. 1, 4, 2, 4, 2, dot, 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 4, 1. So like the trapezoid rule, it starts with 1 and ends with 1. And with the Simpsons rule, the second element is 4, and the next to the last multiplier is also 4. So we can say that the integral from 1 to 9 of f of x dx is approximately 1/3 times the quantity b minus a, which is 9 minus 1, over 8, because there are 8 partitions. And now we have f of 1 plus 4f of 2 plus 2f of 3 plus 4f of 4 plus 2f of 5 plus 4f of 6 plus 2f of 7 plus 4f of 8 plus f of 9. So this integral is approximately equal to 1/3 times 1 times 1 plus 4 times 3 plus 2 times 2 plus 4 times 1 plus 2 times 3 plus 4 times 5 plus 2 times 2 plus 4 times 1 plus 7, which is 62/3. The same result that we had previously when we used the 4 parabolas. Like the trapezoid rule, if the intervals are not of equal width, then we have to use individual parabolas, and that will take a lot of work and is not recommended. Also note that Simpson's rule only works when n is even. If n is odd, it's recommended that you perform Simpson's rule with the first n minus 1 points, and then use a trapezoid rule for the final 2 points. In number 1, you are given selected values of x from 30 to 70 and corresponding values of f of x. We would like to approximate the integral from 30 to 70 of f of x dx, both by the trapezoidal rule and Simpson's rule. For the trapezoidal rule, the base is 5, so the integral from 30 to 70 of f of x dx is approximately 5/2 times 83 plus 2 times 79 plus 2 times 74 plus 2 times 68 plus 2 times 61 plus 2 times 49 plus 2 times 37 plus 2 times 31 plus 33. And that gives us 2,285. For Simpson's rule, there are 9 data points, meaning that there are 8 intervals, and that is even, so we can use Simpson's rule in its entirety. So the integral from 30 to 70 of f of x dx is 1/3 the base, which can be gotten by 70 minus 30 divided by 8, times 83 plus 4 times 79 plus 2 times 74 plus 4 times 68 plus 2 times 61 plus 4 times 49 plus 2 times 37 plus 4 times 31 plus 33. And that gives us 5/3 times 1,368, or 2,280. When you have a lot of data points, this can be done very efficiently on the calculator. You use your stat feature and put the f of x data in L1, and your multipliers 1, 4, 2, 4, 2, dot, 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 4, 1 in L2. You then define L3 as L1 times L2. And then from the home screen, take the sum of L3. The sum is located in the List Math menu. And then finally multiply by b minus a divided by 3n as shown. If you are asked which of these is most accurate, the answer is you do not know. The reason is you are given values of x and no intermediate values of x. So we have no idea what the function does, for instance, at 33 or 48. And it may be that the trapezoidal rule is a better approximation. In number 2, we would like to see how good these formulas are. We are given an integral from 0 to 1 of 4 over 1 plus x squared dx and asked to calculate the actual value of it, and then approximate this value by using the trapezoidal rule and second Simpson's rule, and see the error involved when we use these approximation techniques. The exact value is easy. We are looking at the integral from 0 to 1 of 4 over 1 plus x squared dx, which is 4 inverse tangent of x evaluated from 0 to 1, or 4 inverse tangent of 1 minus 4 inverse tangent of 0, which is 4 times pi over 4 minus 0, and our answer is exactly pi. We will let n equal to 10 subintervals. So in L1, we will put our values of x, which are 0, 0.1, 0.2, ... 0.9, and 1. In L2, we will find y1 of L1. And we see those values 4, 3.9, 604, etc. In L3, we will put our magic multipliers for the trapezoidal rule, which is 1, 2, 2, 2, ... 2, 1. And then in L4, we will do the calculation L2 times L3. So back on the home screen, we get the sum of L4, and then multiply that result by 1/2 the base, or 1 over 2 times 10. And we get 3.1399, etc. And now take a look at pi minus that answer, which is our error, and we get 0.001666647. So it is accurate to 2 1/1000ths. For Simpson's rule, we use the same values of x and f of x, but our multipliers in L3 are 1, 4, 2, 4, 2, ... 4, 1. L4 is still calculated L2 times L3, and you must actually do that calculation again. So back out on the home screen, we take a look at the sum of L4, and then multiply that result by 1/3 the base, or 1 over 3 times 10, and we get 3.14159, etc. Pi minus the answer shows that our answer is accurate to 10 to the negative 8 power. So Simpson's rule is very, very exact. Since not all expressions can be integrated, we frequently must use the trapezoid or Simpson's rule to approximate the value of a definite integral. Since these are approximations, there is an error associated with the trapezoid rule and Simpson's rule. So, if a is the integral from a to b of f of x dx, then if f has a continuous second derivative on the interval ab, then the error E in approximating A by the trapezoidal rule is E will be less than or equal to B minus A quantity to the third power over 12n squared multiplied by the maximum value of the absolute value of the second derivative of x on the interval A to B. If f has a continuous fourth derivative on AB, then the error E in approximating A by the Simpson's rule is E will be less than or equal to B minus A quantity to the fifth power over 180 n to the fifth multiplied by the maximum value of the absolute value of the fourth derivative of x on the interval A to B. Even though we can integrate 1 over x dx, let us use these formulas to calculate the maximum error of the integral from 1 to 4 of 1 over x dx with n is equal to 4. For the trapezoidal rule, the first derivative is negative 1 over x squared, the second derivative is 2 over x cubed. So e must be less than or equal to 4 minus 1 quantity to the third over 12 times 4 squared times the maximum value of the second derivative on 1 to 4, and that will be 2. And our answer is 0.281. For Simpson's rule, the third derivative is negative 6 over x to the fourth, and the fourth derivative is 24 over x to the fifth. So the maximum error must be less than or equal to 4 minus 1 raised to the fifth power over 180 times 4 to the fifth times the maximum value of the fourth derivative on 1 to 4, and that is 24. So our answer is 0.032.